Hello, and welcome back to the course on quantum mechanics. We are still on the 6th chapter for this course. So, before we proceed with this lesson, let us first review the previous lessons. So, in the first lessons, we have discussed about the non-degenerate first-order theory, which gives us the first-order correction in the energy of a perturbed system. And the first order energy correction is just the expectation value of the perturbation with respect to the unperturbed states. So for this lesson, we will be talking about the first order degenerate perturbation theory. So what if now your energy levels, or there are now many states with the same energy, and what is now the first order correction for that perturbed system? So we will consider directly the generic case if you have n-fold degeneracy, wherein there are n states with the same energy En. So from the first order theory equation, which is just an eigenvalue equation for the perturbation operator H prime, it's given by this one. So you will notice that we put a symbol here, a wavy symbol here, to signify that we are representing our operator as a matrix. So we will use the concept of matrices in the first order degenerate perturbation theory. So the Hamiltonian matrix is a Hermitian matrix, so it's an n by n matrix. So assuming these are the matrix elements of your Hamiltonian perturbation matrix, and these are the ket vectors representing the wave functions, and En1 is your first order correction in energy, and we are trying to solve for this one, En1. Now in this case, this is n-fold degeneracy. There are n states with the same energy E. So to solve for En1, you need to solve for the matrix elements of your perturbation matrix, and you do that by sandwiching the perturbation matrix with respect to the degenerate states psi I0 and psi J0. So in order to solve for En1, we use the characteristic equation. So we have done this over and over again, starting with your mathematical physics, and then with the previous lessons on angular momentum, how to find the eigenvalues of the angular momentum. So here we are trying to find the energy eigenvalues using matrix theory, or matrices. So to solve for En1, you solve this characteristic equation. So you subtract the perturbation matrix minus En1 multiplied by the identity matrix. So this is the standard way to solving a eigenvalue equation using matrices. So basically, the characterization is given by this one. So only the diagonal elements of the perturbation matrix is subtracted by En1. So the diagonal matrix elements are subtracted by En1. And then you take the determinant of that. There are many ways to get the determinant of matrix. You can use expansion of the first row method. You can use the basket method. So you utilize those methods. Okay, so let's consider one-fold degeneracy. When you say one-fold degeneracy, meaning that the degeneracy is 1, or in other words, it's non-degenerate. So in that case, your perturbation matrix is just a 1-by-1 matrix, and you only have one element in your perturbation matrix, H11 or HII, and that is basically what we obtained in the first order non-degenerate perturbation theory. So this one, we have derived the first order non-degenerate perturbation theory from the degenerate perturbation theory. Now if you have twofold degeneracy, So you have two states, say psi A and psi B. So we have two states, say psi A and psi B, with the same energy, En. And in that case, we only have a, so this is our unperturbed case, En0, psi A0, psi B0. So these two states have the same energy, En0. Now, if you subject this system into a perturbation, then you will have the perturbation matrix. Since it's twofold degeneracy, then the perturbation matrix is a 2 by 2 matrix, and the characteristic equation will be given by this one. So you have HAA minus En1. So diagonal elements are subtracted by En1. So you take the determinant of that, and in this case it's just actually just easy to take the determinant. It's just a basket method. So multiply this one minus that one and solve for En1, and you get a quadratic equation. So actually, if you have twofold degeneracy, you are expected to have two first order corrections in energy. So there will be two first order correction in energy, En1 plus and En1 minus. So the plus and minus correspond to the roots of the quadratic equation. So in this case, this term here is just basically absolute value of HAB prime, the multiplication of the cross elements, HAB prime and HBA prime, that one. And in general, HAB adjoint is just the HBA prime. So take note, your matrices, your Hamiltonian matrices are Hermitian, meaning if you take the transpose and then the conjugate, so you flip this one, you take the transpose and then you take the conjugate, then these two terms will actually exchange, and meaning the transpose of conjugate or the adjoint of each other is the other one. Okay, so in this case, you can solve it easily, the ENs, the first order corrections. So what happens now? So originally, this is your unperturbed states. You have two states, psi A0, psi B0. They both have the same energy, En0. When you apply the perturbation, there are now two corrections to the energy. One is a plus, one is a minus. So the perturbation actually splits the unperturbed energy level. So there's now a new energy level, En0 plus the first order correction, and then En0 plus the first order correction, the second first order correction. So there are two first order corrections in energy for a twofold degenerate system. So they will now have two new states, psi n plus and psi n minus, and these new perturbed states are actually now degenerate. So, and these new states are actually just from our previous lesson. Basically, the new states are just linear combination of the old or the unperturbed states. So linear combination of the unperturbed states psi A and psi B. And A plus and minus and B plus minus here are just the linear combination coefficients. So in terms of matrices, you can write this as this one. So take note, psi A and psi B0 here are the eigenvectors. You can call them unit vector. They are essentially unit vectors. So I hat, j hat, k hat, that thing, those things. So when you represent them as a matrix, you just use the you just write the linear combination coefficients, A plus minus and B plus minus. So if you take the inner product of the perturbation matrix with respect to these two new states, you must get the first order correction energies, the corresponding first order correction energies. So n plus and minus. Now, these two unperturbed states are orthonormal with each other. So their inner product is 0, which means that these two new perturbed states are also orthonormal with each other, meaning their inner product is also 0. Okay, let's have an example. This example is called a bead in a wire. There's actually a problem in the infinite square well chapter about this, a bead in a wire, because it represents basically its elements or its wave functions are similar to that of an infinite square well potential system. So basically, you have a bead, and it can only go. can go back and forth. It can oscillate within a wire from a length of negative L over 2 to positive L over 2. That's the original problem. Now, what you have now is, you have now a perturbation. So you now have a perturbation. And this is your perturbation, where A here is very much less than the length. So this is equivalent to putting up a dimple or some slight bending at the center of the wire, such that the particle will be trapped in this small bend in the wire here. So you put a small bend in the wire, and this represents this perturbation here. So in the original problem, there's no bend in the wire, so basically it's just a particle in an infinite square wave potential. So in this case, the wave functions are not in terms of sign, but in general exponential, e to the I theta. So these are the unperturbed wave functions of the bead in a wire problem without the perturbation, and these are the unperturbed energies. So if you will notice, it looks similar to the energy and wave function of a particle in an infinite square wave potential. Now, in this case, for this case, the n here actually starts from 0, and then it can have positive and negative values. Positive 1, negative 1, positive 2, negative 2, and so on. Which means that for every energy level, there are two values of n. So for n squared is equal to 4, there are actually two possible values where n squared is equal to 4. It's positive 2, and n is equal to positive 2, and n is equal to negative 2. They both have the same energy. So meaning, your states now can have it's doubly degenerate. So twofold. It's twofold degeneracy. So you have positive n and negative n. So we can actually convert this into two states, psi A, which is positive n, and psi B, which is you have negative n. So in our case here, n is already a positive number, but here you have positive n, e to the positive 2 pi I n x over L, and e to negative 2 pi I n x over L. So we now have two states. These two states have the same energy, this one. So this is a twofold degenerate problem. Okay, how do we find the first order correction in energy? So of course we need to construct the perturbation matrix, HAA prime, HAB prime, HBA prime, HBB prime, and then we solve for the characteristic equation to solve for the energy. And there's actually a shortcut to this. The shortcut to this is this formula for energy. Sorry. So once we know the matrix elements, we can immediately use this formula to solve for the first order corrections in energy. Okay, let's try it. So let's first solve for the first perturbation matrix element, HAA. So I'm just going to go back to my board work mode. So HAA prime is just equal to psi A 0, then the perturbation H prime psi A 0. So AA means you need to take the expectation value of H prime with respect to psi A 0 and psi A 0. So psi A 0 is this one. This is our psi A 0. So if you use this, so we convert this into an integral. Again, this is the integral of psi A 0 conjugate H prime psi A 0 dx. Sorry, that one. Okay, our psi A 0 has a factor of 1 over square root of L. So there are two psi a0. Psi a0 here. There, it's real, so its conjugate is just itself. You have as 1 over square root of L here, 1 over square root of L here, so you get a 1 over L factor. And for our perturbation, you have a negative u naught factor, so we also take that out of the integral, and you will get negative u naught over L. So integral of the first one, this one, is e to the 2 pi I n x over L. 2 pi I n x over L, and then the perturbation, you will have, okay, sorry, this is, sorry, there's an imaginary part here, because there's an I. So if you take the conjugate, then you need to take the I becomes negative I. So basically this becomes negative, so because you take the conjugate of psi a0. And then you get the matrix perturbation, which is e to the negative x squared over a squared. And then for psi a0, the original psi a0 is e to the 2 pi I n x over f. Now these two exponential will actually, you have e to the negative I theta times e to the negative I theta, or you add the two, or you multiply the two, you will get 1, or e to the 0 or 1. So basically, you just have to solve this exponential, e to negative x squared over a squared dx, from negative L over 2 to positive L over 2. So that one. So you look for a integral formula here. This is actually a Gaussian integral, or similar. Yeah, it's a Gaussian integral. If you will recall, we have used the Gaussian integral formula before, so you recall that one, and this will give you a value of, so negative u naught over L. So the answer to this integral is actually a square root of pi. So you recall the Gaussian integral formula. So that's a prime. So this is actually equivalent to HBB prime, where HBB is psi b0 H prime psi b0, where psi b is the second state or wave function. So use that one. Okay, so I will leave the rest of the elements to you. I will leave the rest of the cross diagonal elements, HAB and HBA, to you. Actually, the HAB and HBA in this case are the same. So this is your HAA and HBB element, and this is your HAB and HBA element. Okay, so we now have the 4 matrix elements of our perturbation matrix. So this one, we now know the 4 elements of our perturbation matrix, so we can now solve for the first order correction in energy. And there are actually 2, because this is twofold degeneracy. You will get 2 first order correction in energy. So you substitute all of these values to this equation here. Sorry. So in this case, since HAA and HBB are equal, then this term is 0. So you do that, substitute all of that, and you will get a value of this one. So these are now the first order corrections in energy. So from one energy level, it will now be split into 2 energy levels, because there are now 2 corrections. So from the original energy, which is this one, this will now be split into 2 energy levels. So these are now the first order corrections for the system. Okay. We're also asked to find the perturbed states of a bead in a wire, the problem, or in the of this system. So how do we get the perturbed states? So for the perturbed states, psi n plus and psi n minus, we use this one. So it should be a linear combination of these two unperturbed states. So all we need to find are the linear combination coefficients, a plus and a minus and b plus and b minus. We will start with n, the plus, the upper state, or the upper energy level. So for psi n plus, for instance, psi n plus, this is, you have a plus psi a 0 plus b plus psi b 0. Okay. We need to go back to our original eigenvalue equation. So this is our eigenvalue equation. We start with psi n plus, and this is en plus psi n plus. We need to, so in terms of matrix form, this is a plus b plus. So we already know the elements of this. So you have HAA prime, HAB prime, but HBA prime and HAB prime are the same, so I can also write HBA prime as HAB prime, and since HAA prime is just equal to HBB prime, so I can just write this as HAA prime. So these are the matrix elements of my perturbation matrix H prime. And then this is A plus B plus. This is En plus. We already know the value of En plus. We'll substitute that later. So A plus B plus. So basically, you multiply these two matrices and you will get HAA prime A plus plus HAB prime B plus. That's the first element. Second element is HAB prime A plus plus HAA prime B plus, and this is equal to En plus A plus En plus B plus. So you have two matrices, you equate them, they're both equal, meaning their elements must be equal, meaning this term here is equal to that one, and that term here, or that element, is equal to that element. And you can now solve for A plus and B plus. So you use two equations, two unknowns, and you will get A plus in this case, B plus is equal to A plus En plus minus HAA prime over HAB prime. So if you substitute the results that we have before for En plus HAA prime and HAB prime, we will actually get this value to be equal to -1. So this is actually so you will get negative A plus. So this is actually -1 if you substitute all of these values here. So meaning B plus is equal to negative A plus. So B plus is equal to negative A plus. So therefore psi n plus is now equal to A plus, and B plus is equal to negative A plus. So you take out A plus and then you will get 1, -1. So meaning, in order to solve for A plus, you normalize. So you get psi n plus, psi n plus. So you will get A plus and squared 1, -1, 1, -1. That one. Normalize. And this should be equal to 1. And you will get, this is 1 plus 1, so 2A plus squared. So 2A plus squared is equal to 1, meaning A plus is equal to 1 over square root of 2. So meaning A plus is 1 over square root of 2, and B plus is negative A plus, so -1 over square root of 2. So we now have solved the eigenvalues for the plus, psi n plus. So psi n plus is just equal to 1 over square root of 2, 1 negative 1. That one. Okay. So meaning, it's also equal to a plus is 1 over square root of 2. Then psi a0 is 1 over square root of L e to the positive 2 pi I n x over L. And then b plus is negative 1 over square root of 2. So minus 1 over square root of 2, 1 over square root of L e to the 2 pi I n x over L. And simplify, so you will have e to the I theta minus e to the, this is negative, sorry, e to negative I theta, and that will give you a sine function. Take note, e to the I theta minus e to negative I theta, that's actually sine theta over 2i. And that will give you, simplify that, and you will get a sine function. So I will leave the rest of the details to you. So for the sine n plus, you will get a sine. This is a combination again of e to the I theta minus e to negative I theta. And for the psi n minus, the lower state, the lower energy state, is this one. It's cosine, meaning you have e to the I theta plus e to the negative I theta function. Okay. So that's for example number 1. It's very long. So also you need to check that if you take the expectation value of the Hamiltonian or the perturbation matrix with respect to psi n plus and with respect to psi n minus, you will get the corresponding first order correction in energy. So I will leave this to you. Okay. Example number 2, particle in a box. So you have now a 3-dimensional infinite square well potential. And this is the perturbation. So this is now a particle in a box. So it's now an infinite cubical well. So the width of the well are 0 to a for x, 0 to a for y, and 0 to a for z. But there's now a perturbation. So in the region 0 to a over 2, 0 to x is equal to 0, x from 0 to a over 2, and y from 0 to a over 2, and z from 0 to a. So basically 1/4 of our box is the potential there is unit. So in a unperturbed particle in a box problem, the potential inside is 0. The potential at the boundaries are infinite. But in this case, in one-fourth of the box, one-fourth of the box actually has a potential of unit. The rest, the 3/4 part of the box, is the potential is 0. So the perturbation is only for this region, for the 1/4 region of the box. Okay, so we are asked to find the ground and first excited state energies up to first order correction. So the ground and first excited state energies. Okay, so let's first consider the unperturbed system. So this is the unperturbed wave function, the 3-dimensional infinite square well, or the infinite cubical well. So basically, you have square root of 2 over a sine nx pi x over a sine ny pi y over a. So you have 3 square root of 2 over a, so you have 2 over a to the 3's. That one. So in this case, where nx, ny, and nz starts from 1. So nx, ny, nz here starts from 1. So integer values 1, 2, 3, 4, 5, 6, 7. So therefore, this is now the ground state. So you have the x component of the ground state, nx squared plus ny squared plus nz squared. And kappa is just this value, this constant, pi squared h bar squared over 2ma squared. So the ground state of this particle in a box is when nx is equal to 1, ny is equal to 1, and nz is equal to 1. So this is the unperturbed ground state. So nx, ny, nz are all 1. we will this is actually psi 1110, and we will rename this state as psi 00 to signify that it's the ground state. Psi 00, the unperturbed ground state. The energy of this unperturbed ground state is n is equal to 1, ny is 1, and z is equal to 1. So therefore 1 plus 1 plus 1, so you have 3 kappa. And this is E1110, and I will rename this to E00 to signify that it's the ground state. You will notice that there's only one state in this with this energy 3 kappa, meaning this is a non-degenerate case. So we will use non-degenerate perturbation theory for the ground state, for the first order correction. Now let's go to the first excited state. So I placed there states because there are actually 3. So you can have the first excited state is when one of the values of nx, ny, or nz is 2, and the 2 other values of n are 1. So you have 1, 1, 2. So you have 1, 1, 2, 1, 2, 1, and 2, 1, 1. There are 3 possible combinations. But again, these 3 states, 1, 1, 2, 1, 2, 1, 2, 1, 1, have the same energy, 6 kappa. And I will rename this energy as E10 to signify that this is the first excited state, the unperturbed first excited state energy. And since there are 3 states here, I will rename this, I will rename psi 1120 as psi 1a, psi 1210 as psi 1b, and psi 2110 as psi 1c, to signify that these 3 states are all first excited states, and there are 3 first excited states, psi 1a, psi 1b, and psi 1c 0. So you will notice that this is a degenerate case. There are 3 states with the same energy, E10 or 6 kappa. So this is a threefold degeneracy. So we will use 3x3 Hamiltonian here. So our perturbation matrix here is a 3x3 matrix, because this is a threefold degeneracy, and we will expect that we will have 3 first order corrections in energy, meaning this energy level, so the first excited state energy level will be split into 3 energy levels. Okay, so let's start with the ground state. So ground state, it is a non-degenerate case, so we will use non-degenerate perturbation theory. Okay. So for the ground state, we call the ground state as E00. So the first order correction in the ground state is E01. So because we designated E00 as our ground state. So this is actually just the ground state, which is psi 00. Then your perturbation H prime psi 00. So that one. So our psi 00 is the 111. We renamed our ground state from psi 110 to psi 00. So that one. This is our ground state. So we convert this into an integral. So basically this is the ground state conjugate H prime, the ground state dx dy dz. So this is a volume integral, dx dy dz. This is a triple integral. Okay, so if you go back, our ground state has no imaginary part, meaning the conjugate of the ground state is just the ground state itself. So basically you will just have a square of the ground state. So the square of this, so the square of 2 over a to the 3 halves is 2 over a cubed, and square of each of these terms. And this is our h prime. It's unit, but it's only defined from x is 0 to a over 2, y is from 0 to a over 2, and z is from 0 to a. So how do we do that? Okay, so we have a factor of 2 over a cube, and then we take out the h prime here is u naught, we take it out of the integral, and then we will have 3 integral. So for the x, we have sine squared. So this is nx, ny, nz equal to 1. So you have pi x over a dx. This is from 0 to a over 2. Take note, our perturbation unit is only from, the values of x is from 0 to a over 2. And then for the y, it's also from 0 to a over 2. Sine squared pi y over a dy. But for the z, it's from 0 to a. So you have sine squared pi z over a dz. So that one. So this is just integral of sine squared. So you change variables and then solve for sine squared u du, and you will get a value of u naught over 4. So this is now the first order correction in the ground state. So E0 is the ground state. So this is the first order correction in the ground state. Okay, now for the second problem, for the first excited state, is degenerate. It's three-folds degenerate, meaning we need to construct a 3x3 matrix for the perturbation matrix. So we need to construct a 3x3 matrix. This one, these are the elements. So we have 9 elements. We need to solve for the 9 elements. And maybe I'll just show you one. And you'll do the rest. And after we solve for the perturbation matrix, we solve this characteristic equation to solve for the first order corrections in energy. Okay, let's start with again, I note that we have 3 states, A, B, C, psi 1a, psi b, psi c. So meaning HAA is actually psi 1a, psi 1a. You sandwich your perturbation between psi 1a and psi 1a. And psi bb or psi bb is psi b and psi b, as HCC is psi c and psi c, and so on. So I'm just going to solve one for you. I will let you do the rest. Okay, let's try to solve HAA first, the first element. So HAA prime, this is psi 1a, H prime psi 1a. So AA, meaning psi 1a, you sandwich your perturbation with respect to these two wave functions. Okay. So going back, this is our psi 1a. So you take the integral of the conjugate of this times u naught times this one dx. So basically, you just get the square because there are no imaginary parts of the conjugate. So in this the conjugate, so again, this is integral of psi 1a conjugate h prime psi 1a dx dy dz in this case, because this is a 3-dimensional problem. Okay, so basically you just have psi 1a squared because the conjugate of psi 1a is just itself. So square of psi 1a multiplied by h prime is u naught, but it's defined on different intervals of x, y, and z. So you will get a factor of 2 over a cubed, then u naught, and then for the x part, you will get sine pi x, sine pi y over a. There's a 2 in z. Okay, so you will get sine squared pi x over a dx. This is from 0 to a over 2 because again our perturbation for x is from 0 to a over 2. The same for y, 0 to a over 2 sine squared pi y over a dy. And for z is 0 to a, but for z, take note, the sine squared is 2 pi z over a. Because this is 112, essentially. This is psi 112. We just rename it to psi 1a. But this is psi 112. Okay, that one. And you will get a value of 1/4 unit. 1/4 unit. So that one. So I will leave the rest of the elements to you, and you should get this matrix. So your perturbation matrix H prime will look like this. H11 is 1/4 unit, and then 0, 0. So there are many 0 terms. So 0, 1/4 unit. 16 over 9 pi squared unit, and then 0, 16 over 9 pi squared unit, then 1/4 unit. So this should be the Hamiltonian that you will be getting. So we can actually factor out 1/4 unit, and we can obtain a more simpler version of this. We have 1, 0, 0, 0, 1, k, 0, k, 1. Where k is this quantity, 16 over 9 pi squared. Sorry, 64. 64. Because we take out 1/4. So where k is 64 over 9 pi squared. So this is now our Hamiltonian. So what you need to do next is this one. Take the characteristic equation. So you subtract the diagonal elements by en1. Take the determinant. So it's just easy to use the determinant here. I recommend to use the basket method because you only need to multiply this and to subtract only one term. This one multiplied by that one. So use the basket method. So in doing so, you will get 3 roots. So I will leave the finding the determinant to you. So actually, if you find the determinant of this one, h prime minus en1I will actually look something like this. You have 1/4 unit cube minus this is actually k. So you will have 1/4 unit cube, and then k cube, one-fourth unit cube, and then k cube. Oh, sorry. The diagonal terms are subtracted by en, so you will get 1/4 unit minus en1 cube, then minus this term here. So you will get this is 4k, 1/4 unit. This is 1/4 unit k, 1/4 unit k, and then 1/4 unit. So basically you have 1/4 unit cube, and then k squared. 1/4 unit cube k squared. So simplify that one and solve for en1, the first order correction. Sorry, the first order correction, this is, since this is the ground state, so this is E0, 1. No, E11. We designated E1 as our first energy level. Psi1 is our first energy, first excited state. So E11, first excited state energy correction, E11, and solve for E11. So doing that will give you 3 values for E11. So I will just leave the messy calculations to you, but that is the solution. So this is the ground state first order correction, 1/4 unit. For the first excited state correction, you will have 3. So the roots of that determinant will actually give you 3. You have 1/4 unit to 1 minus k. Again, k is 64/9 pi squared. So you have 3 roots, 3 first order corrections. So what does this mean? We can let this as our E1A, this is our E1B and E1C, the energy corresponding to the new states. So this is the unperturbed state, this is the unperturbed ground state, and this is the unperturbed first excited state, or first excited energy level, 3K and 3 kappa and 6 kappa. Take note, this is K, it's not kappa. Okay, so the ground state is non-degenerate, the first excited state is degenerate. So we used non-degenerate perturbation theory to solve for the first order correction, which is this one. So the perturbed ground state is basically just lifted by an amount of 1/4 unit. So this is the unperturbed ground state, 3 kappa, and this is the correction, first order correction, 1/4 unit. So this is now the perturbed ground state energy up to the first order correction. For the first excited state, it's actually split into 3. So you will have the highest state, psi1c, is this one, the original or the unperturbed first excited energy level, 6 kappa, plus the first order energy correction. So the highest of these 3 energy correction is this one, 1/4 unit 1 plus k. So that's our E1C. And then the middle one is plus 1/4 unit, E1B. And the lowest one is the one with the minus. So 1/4 unit 1 minus k correction. So 6 kappa plus 1/4 unit 1 minus k. So this is our E1A. So E1A is the lowest state corresponding to an energy of psi1A. E1B is the next state. And then E1C corresponding to this state, psi1C. So even though this is the first excited energy level is now split into 3, but these 3 energy levels are actually very close to each other. They are actually closely spaced energy levels, and they thus form a band, and we usually call this as the first excited state energy band, because they form a band. Okay. Okay, so in this example, you will notice again that the perturbation, when you perturb the system, it lifts the degeneracy. So this state is threefold degenerate, and it now becomes non-degenerate. So one state, one energy level. Okay, so suppose in the same example, in number 2, we are asked to find the first excited states of the particle up to the first order correction. So we are actually trying to find these 3 states here, psi1A, psi1B, and psi1C. How do you get these 3 states? So in general, the first excited states can be written as a linear combination of the originally we set this as psi1A, and this is psi1B, and this is psi1C. But we will now go back to our original notation. So it's a linear combination of the unperturbed states. So these 3 states are 112, 121, and psi211. So alpha, beta, and gamma are our linear coefficients. And alpha and beta and gamma are different for psi1A, psi1B, and psi1C. Okay, so from our previous problem, we have obtained this result. So this is our Hamiltonian in terms of unit and k, where k is 64/9 pi squared, and we have 3 first order correction and energies. Now if we want to solve the 3 corresponding states for the new energy levels, we need to solve these three eigenvalue time-independent Schrödinger equations. So the perturbation matrix acting on psi1a will just give you the energy eigenvalue of E1A1, the first order correction in energy, 1a. Similarly, if we apply the Hamiltonian to psi1b, we should get the energy eigenvalues E1b1, the second first order correction. And lastly, if we apply the Hamiltonian, this perturbation matrix rather, to psi1c, we should get this energy eigenvalue E1c, E1c1. That one. So I'm gonna do the first. I will leave the rest to you. Okay. Let's first solve the first problem. So you have the matrix, perturbation matrix acting on psi1a is equal to E1A1 psi1a. So we already know E1A1. It's actually 1/4 unit, 1 minus k. And our Hamiltonian is this one. So this is u naught over 4, 1, 0, 0, 0, 1, k, 0, k, 1. And our psi1a, we don't know its elements. If you will recall, our psi1 should be a linear combination of psi112, psi121, and psi211, or in matrix form, it's alpha, beta, and gamma. So we need to solve for alpha, beta, and gamma. So this is just alpha, beta, and gamma. And E1A1 is 1/4 u naught, 1 minus k, and then alpha, beta, gamma. So in this, the result of this matrix will give us three equations and three unknowns. So you will get, we cancel out u naught over 4 and 1/4 u naught on both sides. Divide both sides by u naught over 4, or multiply both sides by 4 over u naught. And then we have alpha. First element is alpha, 0, 0. Then second element of this matrix multiplication is 0, beta, k, gamma. So you have beta plus k gamma, and then 0, beta, k beta plus gamma. And this should be equal to, so 1 minus k times alpha, that will give you alpha minus alpha k. This is beta minus beta k, and this is gamma minus gamma k, or k gamma. K alpha, K beta, K gamma. Okay. So this means that alpha is equal to alpha minus K alpha, and this one must be equal to this one, and this one must be equal to this one. So from the first equation, you have alpha must be equal to alpha minus K alpha. What does this mean? So this is actually, I'm just gonna factor out again alpha, no? Alpha 1 minus k. So take note, 1 minus k must not be equal to 0, because this is our n. So meaning, the only way for this equation to hold, since the 1 minus k cannot be 0, is for alpha to be equal to 0. So here we get alpha is equal to 0. So for the second equation, you will get beta plus k gamma is equal to beta minus k beta. So you cancel out beta, add both sides by negative beta, divide both sides by k, and you will get gamma is equal to negative beta. So therefore, our psi1a is alpha is 0, beta, and then gamma is equal to negative beta. So that one. So factor out beta, and you will have 0, 1, negative 1. Meaning, we can solve for beta if we normalize the problem. And you can actually solve beta. Beta is actually 1 over square root of 2, similar to what we have obtained before. So you have 1 over square root of 2, 0, 1, negative 1. So that one. So what does this mean? What is now our psi 1a? So from our psi 1a, take note, our psi 1a is alpha psi 112 plus beta psi 121 plus gamma psi 211. So alpha is 0, so meaning beta is actually 1 over square root of 2, and our gamma is actually negative beta, or negative 1 over square root of 2. So you will get 1 over square root of 2, which is our beta, and then psi 121 minus psi 211. So this is our psi 1a, 1 over square root of 2 times psi 1210 and psi 211 0. So we know the expanded version of this. This one you subtract with the expansion version of this one and multiply by 1 over square root of 2. But actually you don't need to do that. This is already enough. Okay, so this is our result, 121 minus 211 for the first state. You do the same for the other states. You solve their corresponding eigenvalue equations, and you get this result. So psi 1b, the second state, is this one. It's just exactly equal to psi 112, 0, which is originally our psi 1b, 0. And this is our psi 1c. It's a combination of psi 121 and psi 211. So that one. So you need to check that if you take the inner product of say psi 1a, h prime psi 1a, you should get e1a1. You should get the first order correction in energies. So that one. Okay, so that is it for this lesson. So for this lesson, as a recap again, the degenerate perturbation theory is a much more general theory, and it can actually accommodate the non-degenerate perturbation theory. So that's the end of this lesson. I will see you again in the next lessons. So goodbye.